Are you able to hear me? Hello?
Yes. Yes.
Okay. And are you able to see the slides?
Yes.
Okay. So let's start. Um, yeah. Someone had asked a question in last session that how the surface reflectance would appear differently in red, green, blue bands. We had seen the infrared band in last lecture. So this is an image from. So this is the confluence of Yamuna and uh, one of the rivers, one of its tributaries. So here is the picture. So here we will try to see. So this is the true color composite image. So if you look on the left side, these B2, B3, B4, B5, these are all the surface reflectance bands. So LC08, it stands for Landsat 8. This is level 2 surface processing. This is 14402 is this is the number of path and row. This is the date of acquisition uh, for 19th January 2023, and this is the date of processing. This number represents the collection. T1 is level 1 and SR stands for surface reflectance, band 2, band 3, band 4 and band 5. So this true color composite shows that this within this patch we have all the water pixels. This green patch over here is the vegetation, and this another river. These are also the water pixels. So let's look how this image would appear in band 2, which is the which is a blue band, and it ranges from 0.450 to 0.515 micrometer. So if you look at the reflectance spectra now, so it is 0.45 to 0.51. So it should be somewhere around here. Right. So in this range, the spectral reflectance. So this is a spectral reflectance curve of water and green vegetation. So we have both water and green vegetation in our image. So we will look in how in different wavelength ranges this these objects will appear. So in this wavelength range, which is band 2, here we see that the difference between the reflectance of um, vegetation and water is very less. So here almost, I mean, the difference between their reflectances is very less. So in the image, we would expect that there is a very less contrast between the water and vegetation pixels. So if we go back to band 2, we see that, uh, yeah. So the water pixels and the vegetation pixels, they are almost appearing similar. In fact, the water pixels are appearing slightly brighter than that of the because of this spectral reflectance of water is slightly higher than that of the vegetation in that patch. Okay, so uh, yeah, now if we look at band 3, the range of band 3 is 0.525 to 0.6. So 0.6 should be here. So this is the green band. Right. So in this range also we see that water has slightly higher reflectance than that of vegetation, and the difference between both of them is not as much. So um both the images would appear almost similar, and the contrast between the water pixels and the vegetation pixels is very less in this image as well. Okay, yeah. So this is band 3. Now in band 4, the range is 0.630 to 0.680. So again we will look at the spectra. Uh, yeah, almost something like this. And this is band 4. So here the within this range the reflectances are kind of changing. So the reflectance of water is going down, and that of the vegetation is going high. But then in this range we will, I mean, we will see that the spectral reflectances would be the average of whatever falls in that range. So this is the image of band 4. Now let's look at band 5, which is the here. Band 5, which is the near infrared band, and it falls within this range 0.845 to 0.885. So right. So in this range, the spectral reflectance of water is almost zero. So water is not reflecting at all. So the water pixels will appear the darkest in this range, in this band. So this is my band 5. This is the NIR band. And in contrast to that, the green vegetation is reflecting at the highest in this wavelength range. So in this range, it would be the easier to see the contrast between vegetation and that of water. So if we go back to this image, the uh, the contrast between vegetation and water is very clear. So the vegetation pixels, they are appearing the brightest, and the water pixels, they are appearing the darkest over here. So near infrared is also considered to be the best band for studying vegetation, because vegetation reflects a lot in this range. So in green also, I mean, uh, in green also there is a smaller peak, but then in near infrared there is a very high reflectance. So the health of vegetation would be so the health of vegetation would be clearly visible in this band. What about, yeah, yeah, the recorded video will be uploaded on YouTube. And apologies about the last lecture. So because of some technical difficulties, there was the sound was missing in some parts of the lecture. So this lecture will be recorded and uploaded on the YouTube. What about soil in band 5? Yeah. So soil also shows high reflectance in band 5. I mean, as compared to other bands. So yeah, soil will also show high reflectance, but then the vegetation will stand out compared to the soil as well. So, do we have any? Okay. So there are some pixels of soil, or these are the sediment pixels, as we can see from the true color images. So let's look at them in near infrared. So here also they are showing high reflectance, and in other bands also these pixels are showing relatively high reflectance. So which is also which can be seen from the spectral reflectance curve again, that soil will have higher reflectance in band 2 and band 3, but in band 5 vegetation will show higher reflectance than that of soil. That's why soil looks slightly less bright than that of the vegetation, because its spectral reflectance is slightly less in NIR, but then in other bands its reflectance is more, that's why it's appearing brighter. Is that clear?
So soil part and vegetation part again, please.
Okay. So did you understand this part?
Yes.
Huh. So, did you understand that between the water and vegetation, these bands are not good for studying water and vegetation together? Okay, I'll explain again. So, yeah, so this is the range of band 2, right? This band. So, in this band, look at the order. The order is green vegetation, then we have water, and then we have soil. So this will be the order in which the pixel brightness will appear. Okay, and if we look at near infrared, here the order will be water, then soil, and then green vegetation. So the reflectance of water is very less over here. So it's not reflecting at all. So if it's not reflecting, then it will appear darker, right? Then soil is reflecting higher than that of the water, but lower than that of the vegetation. So it will appear slightly brighter, and then vegetation is reflecting the highest. So it will appear the most bright. Is it clear?
Yes, it is clear.
Okay. All right, so we will move to the next week's content. So first, so we had not covered lecture 3 in our last class. So first, I will discuss about how DN values and radiance and reflectance, they are all related. So we will look at it quickly, and then we'll move over to solve a couple of problems. So yeah. So this is the let's consider that this is the surface on this is the surface of Earth, which is being irradiated by the sunlight, and then it gets reflected from the surface and is sensed by the sensors in the satellite. So the data which is recorded by the satellite all right. So here it will the detectors in the satellite will measure the amount of energy that the surface is reflecting, and it will measure those values in terms of it will measure that energy in terms of dn values, right? So dn values is the values they unit. I mean, they don't convert it to or if it's 4-bit, then they'll vary from 0 to 15 and all. So we will not able to compare across the scenes the DN value. So if I have a scene from India and I have a scene from say China, uh, but if I am only comparing the DN values, then that will not make any sense because it will depend on my sensor and other factors. So we need to be able to compare these values across various locations or various time. So we process these DN values into radians and reflectance so that we can have some meaningful interpretation from those values. And if when we convert it to reflectance, we will see that the reflectance will tell us about the properties of objects on Earth. So that will be more meaningful than studying only the DN values. So we will see, I mean, what is radiance. So radiance is the yeah. So this is the absolute measurement of all the energy which is being sensed by the sensor. So this includes the scattered energy or reflected energy or anything. So this has the units of watt per meter square per sterdian. Uh, so we convert these DN values to radians first. So DN values are just numbers. So we convert them to the total energy which is being sent. So there would be a minimum and maximum value which the sensor is sensing. So the minimum amount of energy and the maximum amount of energy. So say it's varying between 10 to 200 watt per meter square per sterdian. So we will stretch but yeah, radiance also. Now, when this energy is being directed at the surface, it is affected by, I mean, not all the energy which is irradiated, not all the energy will reach the surface of the earth. There will be atmospheric factors, there will be factors due to solar geometry, and I mean, which will change the illumination conditions on the surface. So because of these factors, the radiance can also change. So to account for those factors, we convert the radiance into reflectance. So reflectance is it's a ratio of total amount of energy received by the surface and that of reflected by the surface. So in that case, it does not depend on the illumination conditions. So that way we will be able. So it takes us closer to be able to compare it in different scenes. So yeah, so let's look at reflectance. So reflectance is um, this reflectance is independent of uh, illumination and viewing conditions. So in reflectance, we have two things. First is uh, TOA reflectance, and second is surface reflectance. So it is only surface reflectance. So it was this surface reflectance that we were looking before in this curve, right? So TOA is top of atmosphere. So this type of reflectance, it's measured at the sensor only. So this is my sun, and this is the sensor. So TOA reflectance will be measured over here. So in that case, there will be effects of atmosphere and all which need to be corrected in surface reflectance. So surface reflectance would be measured here at the surface, in which we take care of all the um, we remove all the atmospheric correction and source sensor geometry, and then we obtain the surface reflection. So the source sensor geometry would be corrected here in TOA reflectance itself. So we will look at that. So reflectance is energy received divided by energy reflected. So let's look at each term is the numerator and denominator. So energy received is uh, when energy is received from the sun, it is measured in terms of E sun incident lambda. So this is specific for each wavelength, and this is mean solar exoatmospheric radiance, irradiance. So this value is given in the metadata itself, or this value is known. It's priorly defined for each wavelength. So yeah, but then the sun. So this value is defined assuming that sun, sorry, assuming that sun is uh, perpendicular to that of the surface. But then this condition is not true all the time. The sun might not always be perpendicular to the surface, and then its position might be varying, right? So we have to account for this varying position. So say this angle is theta. So we have to account for this changed position of the sun, because um, when this when the sun's position, it changes from the zenith. So this vertical line is called zenith. When it changes from the zenith, in that case there will be changes in the irradiance which is being incident on the surface. So this irradiance it will be highest at that of the mm zenith, and then as the angle becomes higher and higher, it will start decreasing. So we multiplied by cos theta to take care of this angular factor. So to take care of the solar geometry. So the energy received terms, it becomes E sun I lambda into cos theta. Or sorry, it's cos z. Z, where Z is the solar zenith angle. So zenith angle is the angle between the line joining the surface and the sun and that of the vertical. Yeah, and also there is one more correction, which is of that of the Earth-Sun distance in astronomical units. So we know that. So this is the sun, and we know that the Earth's orbit is not circular; it's elliptical. And then throughout the year, the distance between Earth and Sun, it keeps changing. So depending on this distance, this mean solar exoatmospheric irradiance, it will also change. So we have to take care of that factor as well. So yeah, so when D is higher, in that case the irradiance will be less, and when it's lower, the irradiance will be higher. All right. So this energy received, it will be inversely proportional to that of the distance square. Yeah, and this energy reflected, so this is the satellite, right? So assuming that this is a Lambert-Eaton surface, the energy reflected in this case will be equal to spectral radiance into pi. So our formula for reflectance becomes, so this is the solid angle formula. So in that, solid angle is equal to this a by r square, and then it would be pi r square by r square. So this gets cancelled, and that's why we have to multiply it here with the spectral radiance to calculate um, the energy reflected per unit solid angle. So yeah, so with all these corrections, our reflectance formula becomes pi into L lambda upon Okay. Divided by d square. And so this is the formula to calculate top of the atmosphere reflectance. So here we are taking care of the solar illumination geometry. So we are correcting all the errors that arise due to source sensor geometry. And now we'll look at how we can correct the atmospheric errors to arrive at the surface reflectance.
So you have written something A by R square. Will you write it clearly? It's bit not visible. A by R square divided by.
All right, its solid angle is equal to a by r square. So here we are calculating the radians per
A quick
solid angle.
clarification. 1 second. See, of course, within this formula, right, I can understand the exoatmospheric irradiance and then zenith angle and also distance. But when we talk about the solid angle, right, at which part this solid angle comes into this picture? I think we have explained, but I missed it.
Yeah, so what happens is we assume that this is a Lambertian surface. So in case of so this is not an ideal surface which reflects in only one direction. We assume that it's a Lambertian surface, and it reflects the radiation that it receives in all the directions equally. So to account for the direction which is in which is towards the sensor, we do this correction. We calculate the radians per unit solid angle. I mean, this is as per my understanding. If it's not clear, I'll check it once again and confirm it in the next class.
Sure, sure. No, that's what you have said is like what you say. It's logical. I can understand, but just wanted to know more about that. See, of course, the exo-atmospheric irradiance, it's acceptable, and then we are able to understand it clear, and then even zenith angle and also distance. But when it comes to this part, right, the solid angle, we want more details. If you could provide.
All right. So these are all the details that I know so far. I'll learn about it more and explain in the next class.
Sure, sure. Thank you.
Okay.
One more quick clarification. See, when we say radiance, I understand radiance is nothing but the irradiance, the total of irradiance what we are getting from source should be equal to the radiance what the surface has received. Probably deducting the atmospheric attenuation, whatever the radiance we get is, the total irradiance is equal to atmospheric attenuation plus radiance. Is it right, the equation, to my understanding?
Atmospheric
No, attenuation means there would be some reduction in the what do you say, the reflex, the radiance, right, or energy.
yeah. So radiance. So we receive solar irradiance, which is incident on the surface. So we need to correct for the sensor and source geometry. So because of the sensor source geometry also, there is a slight decrease in the radiance,
Right.
and then because of the atmospheric absorption, there is decrease in the radiance.
Right. Okay.
Also, there are other factors. We'll see it when we are looking at the surface reflectance. So there are other factors like so there is irradiance due to scattering. So uh, when the solar radiation they hit atmosphere, the layers of atmosphere, because of the particles in the atmosphere, it the radiation gets scattered and again it gets incident towards the surface, which is in addition to what is being incident.
Yeah,
So
yeah, I understand, but I just wanted to make myself clear by asking this question. See, when the irradiance comes in, and then radiance and reflectance, right? So reflectance, when we say here, it's subtraction of scattering energy, emitting energy, absorption energy, right? When we say reflection here, or it includes all these.
yeah, so radiance is absolute energy. So it is in the units of radiance is in the form of energy, watts per meter square per Serdian.
Right.
For reflectance, it's a ratio. So it will be in percentage or it will be in a fraction from 0 to 1, like that. For reflectance, we are taking a ratio of amount of energy which is being irradiated at the surface and energy which is being received at the sensor. And for radiance, it is the total amount of energy which the sensor is measuring.
Okay.
Is it okay?
Yeah, probably I think going forward, I can make myself clear.
Okay,
That's okay. Fine.
sure. All right, so we saw that TOA reflectance is equal to pi L lambda into d square divided by into cos z. Yeah, and now we will convert this TOA reflectance. We'll see how to convert this TOA reflectance to surface reflectance by taking into account the atmospheric correctness. So yeah. Mm, so this is the same diagram. So this is my point at the surface. So we will look at the atmospheric factors. So this is the direct irradiance. Then the incident light, it also hits on various, I mean, different gases or particles in the atmosphere. And then these particles scatter the light, which is also incident on the surface. And there is also path irradiance, where the uh, sunlight it directly reaches the sensor. So that energy is also being measured by the sensor. So that also needs to be corrected. So in this case, uh, surface reflectance. So again, it is the same formula. Reflected energy. We see that we have uh, is an I lambda into cos z divided by d square, and then to this term we multiply with the transmittivity of the atmosphere between Earth and the Sun. So before we did not take care of this transmittivity and all. Now, because we are looking at the atmospheric factors, we will multiply this term by transmissivity of the atmosphere between Sun and the Earth surface. And so, if the atmosphere is totally transparent, in that case, this will be 100%, and then all the radiation will reach to that of the Earth. If the transparency is less, then in that case, the radiance received will be lesser than what is being incident. Also, to this, we add this another term, E down. So this is the diffuse skylight. So this term, and this entire thing is multiplied by tau v, which is the transmittivity between Earth surface and the sensor. Yeah, and then E reflected.
It's the transmissivity between Earth surface and sensor.
Yeah. So when so this transmittivity, it differs for different paths. So we need to take care of the transmittivity between both the paths here. And E reflected.
And that next term is something E plus E something you have written.
This.
Yes, yes.
This is diffuse skylight. So this is because of the other factors, the scattered light and all. Yeah, and the reflected energy will be pi L L satellite minus L path. So the path radiance, which is an excess quantity which we do not require here. So we will subtract the path radiance from the radiance which is measured by the satellite. So this is E reflected. So the formula for surface reflectance will be pi into L sat minus L path divided by tau v into E sun I lambda to cos z y d square into tau s plus E down. So here, all the other things they will be provided in the metadata, but this term, this term, this term, and this term. So we need to find out that how do we measure these terms in order to correct for the atmospheric effects in this to obtain the surface reflectance. So this was explained in the in one of the lectures also. So we have two methods of atmospheric corrections. It's absolute correction and relative. So in absolute corrections, one of the methods is to measure the first is So in this method, the various atmospheric variables such as humidity or water content and other temperature and other variables. So these variables are measured when the satellite is passing over the particular study region, and then in that area these variables are measured, and then they are fed into these radiative transfer models. And yeah, and these models generate all these variables which are unknowns over there. So these unknowns are generated from the radiative transfer models, and these models, they are fed by the data which is collected during the satellite overpass. Or the second one is, it is not practical that in at all the times this we will be able to measure the variables during the satellite overpass. So another thing which is done is that uh, some models are used to simulate the atmospheric conditions at that time, and then so so these models, they simulate the atmospheric conditions during that satellite overpass, and then these variables, they are again fed into the radiative transfer models to generate these variables and then do the atmospheric correction. Or if this is not possible, then there are methods of relative atmospheric correction. So one of the methods is, so at the location of the study area, when the satellite is passing, surface reflectance is measured at that area in situ conditions, and then the it is calibrated with the surface reflectance calculated by the satellite. So in that case, we will be able to remove the atmospheric errors, and actual in situ data will let us calculate, will let us remove the atmospheric errors. Or there is second method. So this might also not be as practical for a regular user like us. So another method, it's based on image-based atmospheric correction. In image-based atmospheric correction, sometimes, so this method, it's not, it does not remove the atmospheric errors completely, but then it can help reduce the atmospheric errors. So there can be various methods of doing image-based correction. So I'll just talk about one of the methods. So it's dark object subtraction. So in an image, so we have different pixels. For this method, we pick the pixel which is the darkest over here. So it should have the lowest values. So it should I mean, if possible, it should correspond to a water body. So that for example, in near infrared regions and all, water bodies will have the lowest reflectance, and then they will appear the darkest. So here the assumption is that the darkest water body will have the lowest uh, reflectance value, and whatever the DN value is appearing for this pixel, it is because of the atmospheric, it is because of the path irradiance. So we just subtract that value and we assume that over this entire region, the path irradiance is constant. So we subtract the same value from all the
Yes,
pixels.
will you repeat that sentence again? Path radiance over that point.
Yeah, so this path radiance, right? So yeah, so this pixel is corresponding to an object which is reflecting the least. So it should have the lowest reflectance value, right? So
Yes, yes,
so this pixel is, so suppose it's a 0 to 255. So this pixel should have the it should have very low reflectance values. So suppose it has values between so suppose it has value like 10. So in that case also it will be on a darker side. So we assume that this should be, I mean, this 10 which is appearing here, this is because of the path irradiance, and the original value of this pixel is ideally supposed to be 0. So we subtract 10 from all the pixels, and that accounts for the path irradiance, the correction of path irradiance.
yes.
Okay. So yeah, these are the different methods which can be used for atmospheric correction and conversion of TOA reflectance. I mean, going from TOA reflectance to surface reflectance. So
See, when you say correction of path irradiance, that means we are reducing the reflectance value, which is directly going from sun to sensor, right?
yes, yes. So this type of correction, it only takes into account the path irradiance and not the transmittivity and other factors.
Okay, but path irradiance also like a term used when the energy is coming from sun to surface, or it's only directly from sun to satellite sensor.
No. Yeah, it is from sun to satellite. When
Okay.
it's coming from sun to surface, then it's exoatmospheric irradiance.
Okay.
Is that okay with everyone? Okay.
Yeah.
Yeah. So this is an example of the. Uh, so we saw surface reflectance before, which is like the last product. I mean, which is all processed product from Landsat. So this is these are the raw DN values from Landsat 8 from different bands B2, B3, B4, B5. So this is a 16-bit image, and their values range from 0 to 2 to the power 16. It's somewhere around 655. Uh, yeah, it's 65536 total values. So it ranges from 0 to 65535. And in our scene, we have values which are varying in this range itself. So we will now try to do these calculations of conversion of DN values to radiance and then TOA reflectance for this band. So we will try to convert these DN values for band 5 of Landsat 8. And yeah, so we'll look at this. So convert the highest and lowest DN values to radians for band 5 in the previous example. So the highest value is 17578. 6482. All right. So this is all the for Landsat we will get the information that we need for conversion from DN value to radians in the metadata file. So this is the format of the metadata file. So this is one of the groups. So there will be multiple such groups having different information about all the bands which were measured in that imagery. So these are the radiance multiplicative factor and addition factor. So for conversion from radians, DN values to radians, we need to have a band scale factor and an offset. So we are working with band 5 currently. So yeah, I'll give you a couple of minutes. You can try doing this problem, and then I can show how it's done. So you can make use of this data and try to solve this problem. Okay, so was anyone able to solve it? Okay.
So basically, when I do for the highest value, it's I haven't calculated it, but I can say the components 17578 into multiplied by 6.3153 multiplied into the power of 3 plus 31.57635.
Yeah, right, right. So we take these two values. So this is the multiplicative factor and this is the additive factor. So for the 17578 minus 31.565. This I was getting around 70. And sir had explained in one of the lectures. Can you say it? All right. And yeah, sorry, it should be calibrated. Yeah, so this is the calibrated, this is the formula for calibrated radians, which was explained in the lecture by sir. So we will try to solve for the same values using the formula for calibrated radian. So this is the metadata information for um, the Lmax, Lmin, and other values. So you can try solving this problem. The values should be around these only slightly different.
What is QCal here?
Uh, QCal.
Yeah.
Yeah, so QCal is the this it quantized cal. So these are the maximum and minimum values of this band. So for band 5, the
Yeah.
minimum value
This
is 1.
DNH and DNHL and DNH is QCal max and QCal min.
Yes, this is QCal min for band 5. This is QCal max. And QCal is the DN value.
Sorry. I mean QCal. QCal. I'm asking.
Yeah, QCal is the DN value.
DN value we haven't given, right? We have given the minimum and the maximum. L min and L max we have given.
Yeah, so we were calculating this for the same DN values. So this is 175.
Yeah, 175786482.
Yeah.
That becomes 17578 is L max, and then 6482 is L min, right?
No. So this is the radiance value. These radiance values, they're measured at the sensor. So these are measured. So they are given here for band 5. We have this is radiance max and this is radiance min. So this will be L max, L min. So here basically we are scaling this range of radiance values. So this is the range, right? From minus 31 to 382. So we are normalizing it with the range of range of dn values, qcal max minus qcal min, and then multiplying it with qcal minus qcal min. So for the dn value of 1, this radiance will be equal to L min, and okay, and correspondingly the radiance values will keep changing. And for qcal, for the highest value of qcal, we will have radiance is equal to L max. So this radiance, it will be distributed between 1 to 6, 5, 5, 3, 5. So for this pixel, the value is, I'm getting 79.433. Okay, it's similar. Okay, let's move over.
So that last term in the calculation, will you please go to previous one? Yes, that last term in the calculation, that is L mean.
Yes, L min. Yeah, sorry, there was no space over here.
Is it you have written minus 31.57 or what else?
Yeah, it's minus 31.57.
Okay, thank you.
Yeah, this. Okay, now for conversion for radians to reflectance. So all the other values are given. We know spectral radiance. So we are doing it for the same values again. So take spectral radiance from the for the calibrated radiance for both the bands. So L, this was 79.433. This was 9.359. Right, so this term is known. The other terms, they are given in this metadata file, and E sun I lambda is equal to 951.76. So you can explore the metadata and try to look for the other terms and try to solve this. And the way to know that your answer is near correct is that your reflectance should be, it should lie between 0 to 1. So here, your D is Earth Sun distance, which is given here. So this is the D, and Z. So there is sun elevation. So to convert sun elevation to zenith angle, it needs to be subtracted from 90. So this is 90 minus 37.44923447. So this sun elevation angle is this angle, and we need the angle with the zenith. So that's why we subtract it from 90.
See, how we get this exo-atmospheric value? Is it from the same data?
Yeah, so this is defined priorly for Landsat band. I mean, Landsat band defined.
Okay. For Landsat 8, this is the standard value.
Yeah, so the thing is, I took this for an example. For Landsat 8, there is a different, uh, so there are different values given in the metadata. For Landsat 8, this exoatmospheric correction is not really required. I took this for the example.
But see, when it comes into the in the examination, right? So this is a value where we can find.
It will be given, like you don't need to calculate it separately.
Okay. So
I
in the
should be
problem
given.
statement
Yeah,
itself, it will be given.
yeah, this should be given. So yeah, for this we have our TOA for the highest DN value. So my value is around 0.41742. Is any getting nearby? Okay. Is someone's mic on?
Yes, sorry.
Okay. Is anyone getting this value?
Facing difficulty with the cos value. See, this one, right? So we have to use the scientific calculator for sure, right? Even for the examination, for the trigonometric.
Okay, I'm not sure about the examination, but it
Okay,
should be allowed. Yeah, but I'm not sure about it.
okay.
Actually, one calculator is provided. Provided means in the screen we can use that one. Last time I appeared one exam, so our calculator was not allowed there. So in this case, in such case, questions should be given accordingly.
Okay.
So the calculator is there in the system.
Yeah, on screen will be there, but on screen doesn't have this trigonometric function keys.
Oh, I think then the questions would be given accordingly. This is for our better understanding and practice. We are doing all these questions.
Okay.
Okay, it's similar. Yeah, so we looked at um, source sensor geometry. We looked at the atmospheric corrections. Now, third is geometric. Okay, the slide is not getting updated. Yeah. So, third is geometric corrections. So, this was explained in detail in one of the lectures. So, we will just look at it quickly and then proceed to do some problems. So, yeah. So look at this figure. This is the figure from the slide itself. This is the sensor, and uh, this is the field of view of the sensor, where um, I mean the total area that it scans in one go, and the instantaneous field of view is the area, is the angle which is made when it looks. Instantaneous field of view is the angle inscribed at 1 pixel. So this is IFOV, and when this uh, sensor is looking down at the nadir, in that case there would be no distortions in the pixel, but away from the nadir, the pixel would get distorted. So the pixel size might increase or it might decrease depending on the uh, depending on this angle. So geometrically, we'll look at the how ground spot, how this formula is derived first. So this is very easy. So this is the FOV. So it's the total area that the satellite can look in one pass. Mm. So this angle would be theta by 2, and this is h. This is the height of the satellite. So this would be tan theta by 2 into h, and because this is only half the distance, the swath width will be twice as that. And at nadir, this is the pixel size. So d is equal to beta into h, where beta is the IFOV. This is measured in radians. and this is height. And of nadir, it gets a little distorted and it's given like this. So say it's at the deviation from the nadir is angle phi, and this is the pixel size of nadir, and this is the pixel size at nadir, right? So in this triangle, we need to calculate the hypotenuse. So cos phi would be h divided by h prime is h sec theta, and into the IFOV. So d is h sec phi into beta. So this is pretty straightforward. So let's do some numericals on this. So calculate the sorry. Yeah, calculate the corresponding values of nadir pixel sizes of the aircraft with IFOV 2.5 millirad and flying at following elevations. So we have H and we have beta, and D needs to be calculated. So this is 1000 meters. So this is 2.5 meters, then correspondingly this will be 5 meters, 10 meters, 40 meters, and 125 meters. So here we see that as the elevation of this aircraft is increasing, the spatial resolution keeps decreasing. So the lower the height of the aircraft, higher will be the spatial resolution. So in last class, we talked about geostationary satellites and polar satellites. Do you remember? So based on this, can you tell which one of them will have higher spatial resolution and which one will have lower spatial resolution? If we assume that IFOV is same. Does anyone remember? Okay, so polar satellites, they generally fly at very relatively lower elevations. So and geostationary satellites, they are at a very high elevation. So geostationary satellites will have a lower spatial resolution, and polar satellites will have a higher spatial resolution if we assume that the IFOV is same. So find the elevation of the satellite with the same IFOV and 30-meter pixel size. So this is also very straightforward. So
please show previous slide?
Is it okay?
No, previous one, that second question.
Yeah, it's getting updated. There is a slight lag. Okay. Can we move forward?
Yes, yes.
Okay, so at 12,000 meters, at nadir pixel size is 30 meters and IFOV is 5 millirad. So find the maximum angle up to which the nadir distortion in the pixel size is less than 1 meter. So we'll calculate this for pixel size is equal to for pixel size is equal to 31 meter, so that we will get the angle within which the distortion is smaller than 1 meter. So pixel size, so this is D. So D is equal to IFOV into H. Yeah, so for off nadir values, we had it's like 5 into beta. Is anyone getting this? So this is at nadir pixel size, which is 30 meters, and this is off nadir pixel, which is slightly distorted, and its size is 31 meter, and then within this range the pixel size will vary between 30 to 31. So we need to find this phi. Is this clear? So this would be on both sides. So till 14.5 degree deviation from the nadir, the pixel size would vary between 30 to 31. So there will be only a small distortion within that angular range.
That last point in the question, it is given that of nadir, will you please go to previous slide? That
Yeah, it's
no, next to next. The problem just you solved. Next slide. Yes. Of nadir distortion in the pixel size is less than 1 meter. Actually, from that you are getting d equal to 31 meter.
yeah. So this is the maximum angle up to which we can go. So it's less than that. I mean angle less than that.
No, that 31 meter, d equal to 31 meter you have taken. At nadir pixel size is given 30 meter, and but here of nadir you have taken d equal to 31 meter. So from that point, whatever given pixel size is less than 1 meter.
Yeah. So when the angle, when the deviation from the nadir is less, then the distortion will be less.
Okay.
So between that range, the distortion will be less than 1 meter.
Okay.
Determine the satellite with the highest spatial resolution at nadir based on their height and IFOV. So just keep in mind that the units are different, so you might need to convert it. Um, did anyone try? Are you getting similar values? You can reply in the chat box. All right, so yeah, this satellite will have the highest spatial resolution. So even if the elevations are different, um, the based on the IFOVs, the spatial resolution can vary. Um, Now I want to talk about relief displacement, but then before that, to solve some of these problems, we need to understand this scale of aerial photograph. So this is very easy. So so this is the real world object space, and this is the focal. So this is the exposure station. So from here the photograph is being taken, and this is the focal length. So the image, the positive print of the image would be formed over here, and then based on the similar triangle. So uh, scale is defined as the so you can refer to Jensen's book, Remote Sensing of the Environment or something. And some of the books are referred in first lecture by Sir. Remote Sensing and Image Interpretation. And then there is Introductory Digital Processing and all. There you can find um, such references. But numericals, there aren't as many numericals in those books also. So you can check on the internet if possible. Yeah, so the scale is ratio between image distance and ground distance. So here in this photo, the scale of this photograph would be AV by AV, and or it can be the focal length by altitude as well. The course syllabus you can find on NPTEL website, I think. Yeah, so let's solve this problem. Find the minimum, maximum, and average scale in this adjacent photograph. So this is the average elevation, this is the lowest elevation, and this is the highest elevation. So as we saw in the previous figure, the scale will change based on the elevation of the exposure station, or it will change based on the relative distance between the exposure station and the point on the ground. So if the points on the ground are at different elevation, then the scale at each point will be different. So for this, so here this total altitude is 20,000 uh, 20,000 feet, and the focal length is 6 inches. So Let's start with the average elevation. So the average scale for this image will be 1:24,000. And similarly for the lowest elevation, it will be and for highest elevation it will be uh, so I hope this is clear. Yeah, so let's look at relief displacement. So
Please show previous slide.
okay, clear. Okay, so in this image we have principal point here. So principal point is the point where the optic axis of the sensor camera, it intersects the ground surface. So this is the principal point, and this is the line of flight. So the aircraft is going this way, or the satellite is going this way. So in relief displacement, what happens is, if the object is away from the principal point, in that case, and if it is if the elevation of that object is above or below the horizontal plane, in that case the objects will be tilted towards or away from the principal point. So here, if this object was closer to the principal point, in that case the side of the object would not have appeared. So this would not have been visible in that case. Only the top of the object would be visible. So like if this building was over here, only we would be able to see the rectangle and not the sides of the building. So here we are able to see the sides of the building as well. So this distance d, this is called the relief displacement.
Ma'am, are you pointing at certain points in that figure? We cannot see the points. Means you are telling this, but which one exactly we cannot see.
Okay, fine. So are you able to see the principal point?
Yes, I can see that.
Okay, and this is the building that I was talking about. So see, this is the
Yes,
roof.
now it is visible. Yes.
Okay. This is the roof of the building, and this is the bottom of the building. So this is also visible in the picture. So this distance is called as relief displacement. So if we have a picture of relief displacement, then there are photogrammetric techniques using which And we need to know a few other things like height of the aircraft, and then this distance between the principal point and top of the object, and the relief. And based on that, we can calculate the height of these buildings. So we'll look at this figure, and then we can understand it better. So wait. Okay, so let me explain it with a figure. So this is my horizontal surface, and this is the object which is elevated above the surface. This is the exposure point from where the aircraft is traveling. H is the height of the aircraft. So both top and bottom of this object will be appearing in the photograph. So if f is the focal length of the camera, uh, this is f. So this is the negative image which will be formed, and on a positive plane it will be equal distance f. So this is the image formed on the positive plane. So these are the 2 points which we were looking at. These 2 points. Alright. So this is D. And this is R. It's this distance. And this will be the principal point or the nadir point. Alright, so in this figure, the ratio of D by R is equal to H by capital H. So if we know all these things, then we can calculate the elevation of the object. So if we know the height at which the aircraft is flying, then using the figure, we can calculate the elevation of that building. So sir, so there was one such problem, numerical problem in one of the lectures. So this is one of the ways of calculating an object's height. So this is another way of measuring the object height based on shadow length. So suppose this is the building from the previous example, and we do not have any information about the height of the aircraft or any other information in that. But if we have the information based on the information about sun's angle, so sun would be somewhere here. So if we have information about this angle, and we have the shadow length, we have the photograph, so we have the shadow length. In that case also we can calculate the height of the object. Okay, So
Please show previous one, please.
so let's do this numerical. So even if we do not know this angle, this tan alpha, we can use this concept to find the height of unknown objects in a picture if one of the heights is known. So here in this figure, this is the condominium. So the height of this condominium is known to us from before. So this is 172.5 feet, and shadow length on the photo is 0.241 inches, and this is the photo scale. So in photo it's these many inches. So on ground it will be yeah. So it will be these many feet. Uh, yeah, it's given over here, sir. 119.65. So we have tan A like here. So we have height divided by shadow height, which is 172.5 divided by 119.65. This is tan A. Now for this building, we only know the shadow length, but we do not know the actual height of this object. So there also we can apply the same formula. Tan A, here height is unknown, and shadow height is 59.1 feet. So this solar angle, it will be constant for for a scene, the solar angle would be constant for all the objects. So we can just equate these two equations and calculate the unknown. So this would be some 85.1 feet. I hope this is clear. Okay, so we will stop here for today's problem solving session.
You told something regarding that solar value. It is same for all scenes. Something. Will you repeat that sentence?
Okay. So see, sun is very far away from the earth, right? So the solar rays that are coming, they will be at the same angle to that of the earth. They will be at the same angle. They will be parallel. The solar rays that are coming, they will be parallel. So this angle, no matter where your object is, so if your object is here, if it's here, if it's here, this angle will be same everywhere. And your shadow will be here depending on the height of your object. Is it clear?
Yes.
So using this relation, we can calculate the heights of unknown objects in a picture. Alright, so we will stop here for today's session. There were some problems about radiometric correction that we will do next time. So please let me know if you have.
Can I ask a question?
Okay.
So, can you say me the difference between dark target method and atmospheric correction by dark object subtraction? Are they same or any difference is there?
Dark object subtraction and what else?
And dark target method.
Dark target method. I mean, I don't remember about the dark target method, but I think, okay, I'll look it up and tell you in the next class. Can you tell me what is dark target method? All right, fine.
Hello.
I'll look it up and tell you. I don't remember.
Yes, I have confusion regarding if they are same or any difference is there. That is why I am asking.
Okay, I'll look it up and tell you.
And can you tell me what are the various atmospheric errors?
Atmospheric errors we just discussed, right? We had the scattering effect, and then there was path irradiance, and then there was transmissivity effect and all.
Okay.
Yeah, this PPT will be shared and the video recording will also be shared.
That aerosol optical thickness, will it come under atmospheric error?
Aerosol optical thickness. Yeah.
Okay.
Okay, we will discuss radiometric correction in the next session. So the Google Sheet was shared with everyone as far as I know. So I had shared a Google Drive folder in the last session also. It's there in the Google Sheet which is shared with you. There is a Google Drive folder with all the PPTs and the YouTube videos. Okay. Let me see. Yeah, this is the drive link. Okay, yeah, the link to the spreadsheet is given over there. Please use that. All right, if there are no questions, then we'll meet next week. Thank you, everyone.